Our research is on thermal barrier coatings, which are high temperature ceramic coatings that are applied on the turbine blades of gas turbine engines that are used in aircrafts. And the importance of thermal barrier coatings is that they increase the operating temperature of the turbine blade past the blade melting point, and they also increase the operational performance efficiency of the aircraft engines. Now, these coatings consist of 3 distinct layers. You have your ceramic top coat, which is primarily called your TBC. You have your thermally grown oxide, or your TGO, and your metallic bond coat. Under realistic turbine operational conditions in flight, because of the large thermal expansion mismatch in these layers, you have the development of large residual stress within these layers, and that has been linked to the initiation of failure mechanisms of the coating itself. So our study, which was a collaborative effort between the DLR German Aerospace Center, Argonne National Laboratory, Cleveland State University, and UCF, have developed a novel measurement technique system to be able to accurately simulate the operational conditions that are experienced in flight, which is mechanical and thermal loading, and to determine the performance of these thermal barrier coatings under these realistic conditions. So what we've been able to do is first create a cylindrical sample geometry, which is shown over here, which is coated with the thermal barrier coating, and this is representative of the turbine blade. And basically, we have developed 2 measurement techniques through synchrotron or high energy X-ray diffraction methods. The first one is grazing, where you pass the X-ray beam through the side of the sample, and the second is through center, where you pass the X-ray beam through the center of the sample, and you're able to capture diffraction patterns or rings, which are shown on the bottom down here. Basically, each diffraction ring represents the atomic plane or spacing in each particular layer. So like the TBC or TGO have different lattice planes that they correspond to, and when these are unstrained, they are circular, these diffraction rings, and when they're strained, they become elliptical. From there, we can determine the strain and stress, or the mechanical properties within this layer that is leading to failure of the coating itself. And another part of this study that's very significant is we've been able to apply uniform heating on the sample to ultimately achieve a thermal gradient, so uniform thermal gradient across the sample with internal cooling, and that is very similar to an actual realistic turbine blade where you have coolant channels for cooling of the internal substrate. So overall, I'd like to thank the National Science Foundation and the NSF Graduate Research Fellowship, as well as the German Science Foundation, and the Advanced Photon Source at Argonne National Laboratory, where we collected all this data. And I'd also like to close by thanking Graduate Studies for giving me this opportunity to present my research. Thank you.